Hello everyone and welcome back to a new video in our tutorial series talking about Autodesk Robot. Now this video seems to be independent from the current ongoing reinforced concrete modeling analysis and design series, but it is actually connected. I want to explain a quick principle that we have seen in our previous video, which I will be linking on the top right. And the principle or the concept we have seen in our previous video was that it seemed that our structure was twisting. Now, don't freak out. I actually increased the scale of the deflection to be able to see that. But it seems our structure is twisting and turning. And this is something that people just seem to ignore or not even think about. So today I want to talk about the reasons why those structures are twisting and turning, because understanding the reasons is going to be key for the solution of this problem, which we'll be doing in the next video. So in this video, I'll be discussing why those twisting and turning happens in a structure and try cast a light on the reasons and give you a proper understanding of that. Now for that, I will be using an independent structure because this is so interconnected that each one will take ages to perform, and I'm gonna do some tests. So I will do me a separate structure. That's why I'm saying this is kind of disconnected and connected to the reinforced concrete building design tutorial or series. So with that being said, I hope you enjoy. So sit back, relax, and enjoy the show. Alright, to explain the idea of twisting structures, as I said, I will be opening me a new structure and starting with a clean slate. Now, first of all, I want to show you why this twisting happens. So I will be selecting a building design project, and I will do me a very simplified structure. This is a very quick one, and I once again assume that you know how to deal with Autodesk Robot. If you don't, I will be linking a playlist where all my tutorials are there on the top right corner. So here I will just go to my axis here. I will define me, I don't know, like 3 axes in the X at distances of 5 meters. So I have 0, 5, 10, 15. And maybe 4 axes in the Y at distance of 4, and just add that. And the Z, you can say it applies a story system with 0 and 3.5. I'll apply that and close and go to view, and this is my structure. To start with, I'm going to draw me a column. The column is going to have a section of reinforced concrete column of 300 by 500. I'm going to draw that. Notice I am not applying any inertia reductions. My point here is to show you something in the finite element method itself. So I am not applying any moment of inertia reductions. That's not my point today also, but you still know why we do that. We do moment reduction to basically account for cracked sections. So I just quickly do that. I don't think I need to speed this up because it's not that time consuming. So those are simple columns. If you click on the section, you can see them 300 by 500. Fantastic. Now I need to do me some quick beams. Once again, I select my reinforced concrete beam. I'll take the 300 by 500 and start drawing. I'm gonna drag, so let's just do this very quickly. I'll hit the escape button to cancel the drag one time and continue clicking. Hit escape, and once again. Now there is nothing new in this. I hope you're getting bored, which is a good thing, but the fun starts in a moment. You see, I was thinking about doing this on the reinforced concrete building itself, and when I did my first impressions of how fast my video would be, it was dragging too long, and I basically respect your time, so I want to make a simple structure. Okay, so I have beams, I have columns, and they are connected via rigid joints. So it's a 3D frame now. And I'll go to my thickness 300 here for a shell and make me a plate or basically a slab. Now I'll go to my load cases, I'll add me a load, and I'll go to my loads here and add me a surface load of 3 kilonewtons per meter down. Dead live, not my point now, so dead or live, not my point. So I'm done. What do I need to do? I go on story here, right click, stories, copy story, and make me 10 copies of that thing. And there we go. We have our structure. It looks kind of cool, but we all know that this is not impressive. Everybody should be able to do this. If you are unable to do this, please check out my previous videos or ask in the comment section. I usually reply I'm usually active there and reply as soon as I can. I run the analysis, so the structure is being analyzed, and you can see the mesh are working hard. Let's wait until it ends. It's not going to take long. So, okay, it's got analyzed, and I click on the displacements deformation, and you can see the structure deforming vertically. Like if I open the deformation and close, you can see the structure deforming vertically. There is no sideways motion. How do I know that? If I go to top and enable the deflection, nothing changes. If I go to the side or front and take a close look on a sideways motion left-right, if I open the deflection, you can only see a vertical movement. Don't be nervous because of those. The internal beams deflect more than the external beams, so that's perfectly fine. But you can see there is no sideways motion in the structure. That's from the front side. What about the left or right side? Same thing. It's perfectly vertical. There are some sideways motion, but there is no generalistic sideways swing. So this is what you would expect. Like if somebody tells you, hey, I have a structure with gravity loads, you would think, okay, deflections are vertical, and there is no significant deflections horizontal because there are no horizontal forces applied. Or so you thought, because in reality, vertical loads can produce sideways motion. And this is what happened in our structure. And to explain that, I need to show you a little trick. Now, I want to give you immediately the answer. The answer is there is a sideways motion or twisting motion or whatever because there is an unsymmetry in the abilities of the vertical load-carrying elements with respect to the center of gravity of the slab. This is the short and quick answer, but it would not be a CEE channel video if I don't dive into that. So let's dive into that. I'll open the cross sections. You can see the cross section of the column. And now I will do something very simple. I will select my columns here. So I'm holding the control button and selecting all the columns in that direction or in that line. And now I will go to my section. It was, I think, 300 by 500. Let's go to, what section? 600 by 600? Fine. Let's apply that. So now the sections of the columns on the right line should be larger than the sections of the columns on the left side and the center. You can see the right line columns here, those dudes. You can see those guys being bigger than the other columns. So here is the thing now. Now you would think that, okay, it doesn't matter because I have vertical forces, and vertical forces should cause vertical displacements. No, that's not the case in this case, because our vertical load-carrying elements are not symmetric around the center of gravity of that slab. Let me run the calculation to show you. And there we go. So I've run the calculation, and now the moment of truth. If I open the deflection, you can see the tower leaning on the left side, which is amazing. Like there is no horizontal force. I swear, here are the forces. They are purely vertical, as you can see. Yet those vertical forces caused the tower to lean to the left. Why is that? A quick explanation that still needs to be further elaborated is that your vertical load-carrying elements on the left side have a weaker stiffness than the load-carrying elements on the right side, which means that the left side goes down more than the right side. Look at this. The deflection of the left side down is more than the deflection of the right side down. This causes a tilt in the structure, which makes it tilt towards the weaker elements. Now, the problem here is compound, because if the structure tilts, then suddenly, you have extra moments on the columns that were not accounted for because of the P delta effect if you want to do a second order analysis. I might think about this in the future of this reinforced concrete series, but just saying that, hey, this is one case. Now notice, that's not a twisting action, that's a leaning action. But what is a twisting action? A twisting action is a leaning action in two directions, like this leans like this. Twisting can be derived from leaning. If you lean each quadrant differently from the other quadrants, you get twisting action. Now, I will not be able to do this here because I would need unlimited number of tries to do that, but I will show you something else interesting. You see, because it's strong on the right side, the structure leans on the left side on the weak side. What happens if I further increase the unsymmetry? If I go to the sections again this time and select my 300 by 500 and basically select those to put them back to 300 by 500. So I'll basically heal and basically get them back to 300, 500. So now if you look at the structure, all the columns are the same with exception to those dudes. Those dudes are not the same. Those columns that I selected are not the same as the rest. Now, you can pause the video and expect or predict the leaning of the structure. So you should pause the video right now and predict how the structure would lean given those unsymmetries. A small hint, you should think about left-right leaning and back-forth leaning. So I'll let you think about this while I run the analysis. I hope you were able to predict that. Okay, moment of truth. Clicking on this, you will see leaning towards the camera and to the left, and you can see it happening here. The tower, if I go to top, you can see the leaning clearly. The tower is leaning to the right and leaning down, and you can see some twisting motion. You can see some twisting motion that can be compounded later, but the idea is that this unsymmetry of the load-carrying elements makes the structure lean. If you go to front, you can see it's leaning to the left. If you go to left, you can see it leaning to the front. And this is basically why you have leaning elements. But I said something, and I want to further qualify that, because I know some of you are finite element method nerds, so I need to be a little bit careful here. It is not only the vertical stiffness that causes the leaning, it is also the interconnectability, it is the interconnection, it is the rigid joint that makes the structure lean. What I'm saying is, the reason why the structure is leaning is not only because the left side columns are weak, it's also because the beams and the left side columns are connected via rigid joints. Because otherwise, the entire structure would not lean, but the plates would be inclined. I will go first of all here, remove the deflection, select my columns and get them back to big columns. So I select those three columns, or those multiple columns. So I selected my columns now. You can see them selected, and I'll go to the section and make them big again, so that I have one pure mode of basically sideways movement. I will run the analysis now. Wait, did I change them? I think I did. I run the analysis now and see what happens. Now, since I changed the entire line of columns, there should be only a pure movement to the left. So if I open the deflection, yep, wait, what? Did I change? I think I changed that. Let's go to top to understand. Yes, it's a pure movement to the left. There is nothing up and down. Okay, now this should make sense, and allow me to show you what happens now if I remove the connection between the beams and the columns. How do I do that? By releasing. What I'm saying is that another reason why the structure leans, so the structure is leaning to the left not only because the vertical stiffness is different here, but because there is a connection between the columns and the beams. If you eliminate the connection between the columns and the beams, the structure will not lean. So let's try that. Now you could make some releases. I have a better method of doing that. First of all, I'll select all my columns. So right click on column and say select all. I'll go to geometry. Now you could make releases. That's perfectly fine. Where is it? Here. I'll go to additional attributes and open advanced member properties and ask it to become a truss member. So only axial forces, no shear, no moment, no nothing. I'll just remove this to allow for both cases, tension, compression. I'll hit the apply button, and now I'll run the analysis. Please notice now the structure is unstable because I made a house of cards. If you have a column that is released on top and bottom everywhere, this becomes a house of cards. Now, of course, it's unstable, I know. Let's just continue. Now, by the way, this is incorrect. Yeah, what we're doing here is actually incorrect. You cannot just analyze a house of cards. But I'm doing this for the understanding value here. So if I go to deflection, you can see the structure, although it is unsymmetric, suddenly the structure doesn't lean. There is no leaning in the structure. But you can see that the column on the left side is going further down than the column on the right side. However, there is no leaning in the structure. Why is that? To understand why this is, I want to make something very strange. Because it's somehow obscured with the bending of the beam. But what happens here is actually that if the beam is infinitely stiff, you would have a line connecting those two things because it's released here. To understand what I'm saying, I want to do one final thing. I want to go to the section here and define me a ridiculously big section, just saying. So I'll select section here. It's a reinforced concrete beam, and I will say 300 by 1,500. This is a ridiculously big section, just to serve a purpose here. I right-click the beam, select all, and apply that section to the selection. Section selection, it rhymes. Now, of course, I'm ending up with this abomination, but let's ignore that for a moment. Let's run the analysis and see what happens with the structure. Once again, this is an unstable structure. This is an unstable hypothetical structure, and the idea is that I want to understand something in science. You can see it get better and more understandable. Let me just remove the sections so that you can see it. See, it's like the entire slab is rotated, but the structure is not rotated because there is no rigid joint. What I'm saying is, yes, the slab has rotated slightly. Instead of being horizontal, it became rotated, but it did not force the column to rotate with it because you don't have a rigid joint. And because we don't have a rigid joint, the structure remained vertical. If I had a rigid joint, this entire slab would cause the beam to rotate, causing the entire structure to incline. So this, ladies and gentlemen, is the real reason why you have twisting and turning in a structure, even if you load it perfectly vertical. Now, once again, I want to say that this is some sort of a theoretical video I needed to do, but it's very important that I cover that because I intend to solve this issue in the real structure in the next video. So we need to understand why this happened to understand what the solution is. Now, truth to be said, it's impossible for me to totally eliminate the twisting in a tower. That's ridiculous because it's very hard for me to give 100% symmetric columns around the center of gravity. That's very hard. You could say that I am going to use a released system. This happens in some countries where the column is released from the beam and the lateral loads are carried by the shear walls. In that case, you have less to worry, but I will just try to solve this issue with our structure, where the columns and the beams are monolithically cast, or at least, where the columns and the beams are rigidly connected. So that's basically a good introduction to that topic. The point is, you should have a symmetric, as much as you can, symmetric load-carrying characteristics around the center of gravity of the slab. I will not be able to totally eliminate the entire rotation. If you open top and take a look, this is now, of course, no deflection, no sideways motion. So I'll go to geometry and I'll go to additional attributes and to advanced bar properties. And now I need to undo what I have done. So I will right click on the columns. I hope I'm able to do that. Let me see. Select all. And I want to remove this and apply. Yep. And now I will select all the beams and undo that by going to the section, selecting the 300-500 section. So I'm back to my starting position. Let's run the analysis, and I should have a tilting structure to the left. And I want to say something important here, that in our case, it looks scary, but it might not be. What I mean is, well, let's take a look. This is node number. Let's see. Let's open the node numbers. Oh God, I don't know what this is. Let me see. Yeah, this is node number 248. If I go to results, deflections or displacements, it was 248. So let's take a look on 248. There we go. There it is. And I'm surprised. The deflection X is actually worse than the vertical deflection. I'm surprised. This is one of the extreme cases. Like, I'm used to seeing that the vertical is the one that controls and the horizontal is smaller. It turns out no. It turns out in our structure this time, the vertical is less than the horizontal displacement. So I stand corrected. That's something I should learn, and I have done that. So okay, that's basically a quick rundown of the twisting and turning of a structure from vertical loads, why it happens, and how we could basically modify it to not happen. The modification is not easy because you need to have double symmetric, which is very hard to achieve. And this is something I want to finish my video with, because next time we'll be working on our big tower to try make it as less twisty as possible. Spoiler, it's impossible to achieve 100%, but, well, we try our best. So yeah, that's everything I wanted to talk about today. I hope that you enjoyed the video. And of course, before I finish, I want to give a huge twisty tower-like shout out to our dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve. And for that, I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. Of course, if you have enjoyed the video, then please like, share, comment, and subscribe, as a sacrifice to the YouTube algorithm overlords, especially subscribing, because it helps also spread the word and increase the reach of my channel. With that being said, and as per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.